Welcome back to Employability Improvement Training. I am Ramachandran. I am from Buffalo Industrial Technology Research Institute. In the last video, we saw the invention of binary numbers and ASCII code, Unicode formed the basis for processing numbers and language in the modern computers in zeros and ones. Invention of Boolean logic, Boolean algebra, and the invention by Shannon that Boolean logic and Boolean algebra can be implemented using electronic switches resulted in the invention of logic gates and logic circuits, which are used in the internal processing of the modern computers. We also saw that till 1940s computers were fixed form computers or program controlled computers, and advancement in theoretical computer science paved way for storage controlled computer where program and data can be stored in external memories such as RAM or external hard disks. We saw that in the field of computer science, Alan Turing invented Turing machine, which described a simple form of computer, and in 1945 John von Neumann described the computer architecture. Von Neumann architecture first showed that the program and data can be stored in external memory such as RAM and executed in a central processing unit. Von Neumann architecture is also known as von Neumann model or Princeton architecture and had the following subdivisions. It had a processing unit which consisted of an arithmetic logic unit and processor registers. It also had a control unit which had an instruction register and a program counter and generally computed the operation of the processor. It also had a memory to store both data and instructions and external mass storage like hard disk. It had references to input-output mechanisms. In the von Neumann architecture, both data and instructions are stored in external memory and were accessed using a common bus. Under pure von Neumann architecture, CPU will be either reading an instruction or reading or writing data from the memory, as the bus was shared between instructions and data. Both cannot occur at the same time since the data and instructions were using the same bus. A new architecture called hardware architecture was proposed, where instructions memory and data memory were separated and accessed by the control unit using separate buses. This enabled the CPU to read an instruction and perform a data memory access at the same time. This was possible even without a cache. The separation of instruction memory and data memory increased the instruction fetches and data access, and the CPU could run faster as there is no contention for the single memory pathway in von Neumann architecture. Hardware architecture machine had a distinct code and data address space apart from the data and instruction buses. Instruction address 0 was different from data address 0. Instruction address 0 might identify a 24-bit value and data address 0 might indicate an 8-bit value, which was not part of the value pointed by the instruction address 0. Later on in time, a modified Harvard architecture machine was proposed. This relaxed the strict condition that instruction and data separation while still letting the CPU to concurrently access the two memory buses. The most common change was the separate instruction and data caches backed by a common address space. When the CPU is executing from the cache, it acted like a pure hardware machine with the two different instruction and data buses and two different address space, but when accessing the main memory, it acted like a von Neumann machine. This facilitated that code could be moved around like data, which was a powerful technique in programming. This modified hardware architecture is used in modern processors such as Intel x86 and ARM. An instruction set architecture refers to the visible programming interface of a microprocessor. It includes the native data type defined by the processor, the instructions itself, and the registers visible to the programmer, and addressing modes, the memory architecture, interrupt and exception handling, and the external input-output mechanism. An ISA also specifies the set of opcode instructions and native commands implemented by that particular processor. The first ISA that was used is called the complex instruction set computers. It was not named as complex instruction set computer at the beginning. When later on the reduced instruction set computer architecture appeared in the scene, this was named as complex instruction set computers. In the earliest stages, the goal was to give easy programmability for machine language programming and assembly code programming. So instructions which could do operations which are now supported in higher level programming languages were provided in the processor instructions itself. That's why it's called complex instruction set computers. It is a common misunderstanding that CISC systems have more instructions, but they pay a steep performance penalty for having more versatile commands. CISC systems actually have complex instructions which mimic programming constructs which are supported in higher level languages. An instruction in CISC took long time to execute. For example, a double indirect addressing mode required 2 memory cycles to execute. Few CPUs had string copy instructions that required hundreds of memory cycles to execute. Intel x86 is an example of a CISC computer. The CISC programmers were assembly programmers friendly. Instructions in CISC computers had 1 byte to 6 to 8 bytes. This variable length of instructions caused problems in prefetching and pipelining of instructions. Instructions involving arithmetic logic unit had operands which were memory locations. The number of cycles required to access memory location varies. This caused the number of cycles required for the whole instruction to execute also vary. This was not good for the compiler writer and pipelining and other issues. Most of the instructions involving arithmetic logic unit had only 2 operands, where one of the operands is supposed to be the destination after the execution. For example, add register 1 to register 2 and store the result in register 1. This meant that the operand in R1 was destroyed after the execution to store the results of the execution. If you wanted the value in R1, it had to be stored somewhere before running the instruction. Later on in time, reduced instruction set computer ISA was introduced. These systems were misunderstood that it had a small number of instructions but make up with a faster hardware. The initial RISC system had reduced instructions. The reduced instructions essentially mean each instruction does very little and had a minimum of semantic complexity and had higher encoding regularity and simplicity. It took very little time to execute it as it does very little, and the instructions were uniform, hence they can be easily fetched, decoded and executed in a pipeline fashion. This resulted in faster throughput and more optimization in implementing the set of reduced instructions in hardware. MIPS and PowerPC, Alpha XP and Spark are examples of RISC computers. Let us see how an operation is performed in RISC and CISC computer. Let us take this example. Assume we want to multiply data in 2 memory locations and then store it in one of the locations. For example, we want to multiply the data in address 12 and data in address 2 in memory and store the result in memory address 18. In CISC computers, this could be done with a single instructions, as CISC computers supported complex instructions. This instruction takes a long time to execute. It fetches the data from memory and execute the multiplication, then stores the result in the address space 18. The same thing when done in a RISC processor has the following instructions. First, the value in memory location 12 is loaded into register A, and then the value in memory location 18 is stored in memory location B. Then the registers A and B are multiplied. Then the result is stored back in memory location in address 18. This looks like a lot of instructions than what is given in sys, but each instruction required only one clock cycle to execute. Since it was uniform, very efficient pipelining was possible. The entire program may execute in the same time as in a sys processor, but optimization of a small set of instructions in hardware was possible in this architecture. You can notice that in the early days of evolution of computer, when programs were written mostly in assembly language, naturally the effort was in providing complex instructions which were programmer friendly. So the sys started adding more and more complex instructions. Later on, the developments drove the industry towards more efficiency, resulting in the RISC computer architecture. Programs written for one processor cannot run on processors for any other architecture. Current architectures include Intel's IA32, which is also known as x86 architecture, IA64, and ARM, PowerPC, and Spark. Some of the old CISC architecture like Intel x86, in their latest processors, I think starting from Intel 486, had something called an RISC core, where a minimal set of the complete instruction set was highly optimized and all other instructions were implemented using the optimized RISC core to support backward compatibility. So these processors have an RISC core and a CISC cell, which takes advantage of the RISC architecture while still supporting the backward compatibility of the CISC architecture. Microarchitecture refers to the way an instruction set architecture is implemented in a processor. Two processors can have the same instruction set architecture but choose to implement them in different way. Microarchitecture's features include cache memory, pipelining, out-of-order execution, superscale RSU, and branch prediction and multi-threading, etc. In a one-man machine, an instruction cycle had the following operations. The instruction had to be fetched from the memory, decoded by the control unit, then executed in the arithmetic logic unit, and the result is returned back to the memory or register wherever it had to go. Reading from the external memory was slow. This caused a delay in getting the required data to execute an instruction. During this time, the processor remained idle for most of the time. So the goal was to increase the effective speed of the program. After a lot of research, pipelining, cache, large register sets were added to the processors to improve its performance. When the instruction cycle executes sequentially, fetch takes one cycle and decode takes another cycle. The instruction is executed in third cycle and the write happens on the fourth clock cycle. So effectively each instruction took 4 clock cycles. To improve the throughput, pipelining was introduced where circuits were added to do multiple things simultaneously during the same clock cycle. For example, when instruction 1 is fetched and getting decoded in the second clock cycle, instruction 2 was fetched from the memory. While the instruction 1 was executing in the arithmetic logic unit, the instruction 2 was getting decoded in the control unit, and instruction 3 was fetched from the memory. In the fourth clock cycle, when instruction 1 is writing into the memory, instruction 2 was executing in the arithmetic logic unit, instruction 3 was getting decoded in the control unit, and instruction 4 was fetched from the memory. This increased the throughput of a program even when an instruction took the same time to execute. You can see that still an instruction takes 4 clock cycles, but the whole throughput of the program is greatly improved. Pipelining cannot help when branches appear in a program. Till the register in which the condition for the branch is read, the processor cannot decide which branch will be followed. Modern processors with high clock speed supported up to 20 stages of pipeline instructions. When a branching happened, the pipeline had to be flushed and instructions from the new branch had to be built up in the pipeline. It is estimated that every fifth instruction executed in a processor is a branch. This created a lot of stall in the processor, and the processors remain idle while the new pipeline is getting built. A new technique called branch prediction was introduced to improve the performance. An educated guess was made about which branch will be taken when reading the register, which decides the condition. Complex statistical prediction on previous branch designs were taken by the hardware with good accuracy. When the guess or the predicted result is right, this improved performance, but it had the penalty of when the guess is wrong, the pipeline has to be again flushed and built. CPU cache is used by the processor to reduce the average time to access memory. Copies of data from frequently used places is stored in the cache. Cache memory is located on the chip, but it is not a register. Since it is on the processor, data can be made to appear in few cycles compared to the external memory, which takes many cycles to get the data. The CPU includes a cache controller. When the processor needs to read or write from a location in the memory, it first checks with the cache. If the data is in the cache, it immediately reads from the cache or writes into the cache if it is available. If it is not available, a cache miss is fired and data has to be read from the memory. Most modern CPUs have at least 3 independent caches. One is instruction cache and the data cache to speed up data access, and the translation look-aside buffer, which speeds up the virtual to physical address translation for both data and instructions. The cache miss still stalls the processor. When data is not in the cache, it has to be fetched from the memory. At these times, there may be other instructions whose data is available in the cache. Out-of-order execution is a process which allows the instruction whose data is already available in the cache to be executed while CPU is waiting for the data from the memory for the other instruction. The results are then reordered so that it appears that everything was executed in the programmed order. This technique also is used to avoid operand dependency stalls, where an instruction waits for the results of a long latency operation such as floating point conversion or multiple cycle operation. Superscalar processors implement instruction level parallelism within a single processor. It executes more than one instruction by what is called a redundant functional unit. A redundant functional unit is not another core. It is an execution resource such as multiplier, arithmetic unit or floating point units within the same core. So a same core have multiple number of floating point units, arithmetic logic units, multipliers which takes multiple instruction cycles. The hardware looks for data dependencies at runtime and runs multiple instructions at the same clock cycle. For example, if multiple instructions had floating point data, floating point conversions can be run on the multiple floating point units and the data made available for the execution in lesser number of clock cycles. When a processor stalls for data to arrive from the memory, another program or thread which is ready, which has all the data to run, can be scheduled to run on the processor. This is similar to the multi-threading at the operating system level, but done at the processor instruction level. Simultaneous multi-threading or SMT is where more than one thread can execute in any given pipeline. It requires ability to fetch instructions from multiple threads in a cycle and larger register files to store data for multiple threads. Hyperthreading is Intel's proprietary SMT in which the logical cores appear as a processor to the OS. The OS can schedule two processes simultaneously on each of these logic cores. So in the field of computer science, from fixed program computer The model was changed to stored program computer, where the program is stored in memory. Von Neumann architecture was proposed by von Neumann in 1945, which had the same data path, and new Harvard architecture was proposed, where the data path for instructions and data were separate, improving the speed of the execution, and instruction set architectures which satisfied the need of the time, like SIS providing easier programming interface by supporting complex instructions, and later on moving on to RISC, which supports pipelining by having uniform instructions, thereby improving the efficiency of the processors greatly appeared. We saw techniques like pipelining, cache, multithreading, superscalar, which improved the processing throughput and processor speed and the efficiency of the processor. In detail in this class, we will see about microprocessor components in the next class. Thank you.